Radiation heat transfer. This chapter discusses heat transfer by radiation as a mechanism that does not require a medium. The main focus is how thermal energy is emitted by surfaces due to their temperature. Radiation becomes very important at high temperatures and in vacuum conditions. Understanding this concept complements conduction and convection in heat transfer analysis. The discussion is linked to engineering applications such as furnaces, power plants, and thermal systems.
Lesson Plan: Heat Transfer. This material places radiation as an advanced topic after conduction and convection. The chapter sequence shows that radiation requires prior understanding of energy balance and basic heat transfer mechanisms. Radiation has unique characteristics because it depends on surface properties and geometry. From the core structure, this topic is clearly integrative. This helps build a complete picture of heat transfer systems.
Learning outcome. The learning outcomes emphasize the ability to calculate view factors and radiative heat transfer. Students are expected to analyze systems with black, gray, and diffuse surfaces. The radiosity concept is used for multi-surface systems. Geometries such as parallel plates, cylinders, and spheres are key applications. In addition, radiation shields and temperature measurement effects are also highlighted.
Radiation heat exchange overview. Radiative heat exchange strongly depends on the relative orientation between surfaces. Energy emitted from a point or a surface is not distributed uniformly in all directions. The view factor is used to quantify how much of the radiation reaches another surface. This concept shows that geometry plays a central role in radiation. Therefore, radiation is not determined only by temperature, but also by surface position and orientation.
View factor geometry. The view factor is determined by the relative alignment of surfaces and their viewing angles. The distance between surfaces affects the received radiation intensity, which decreases as the distance increases. The analysis is carried out using differential area elements on each surface. This approach makes the formulation general for many geometries. Therefore, the view factor is purely a geometric quantity.
Check your understanding. Number 1. This question emphasizes that radiative exchange depends on the distance between surfaces. Physically, the farther the distance, the smaller the fraction of radiation that can be received. This is consistent with energy spreading in space. This concept is important for estimating system scale effects. This understanding becomes a basis before using view factor formulas. Self-view factor. The self-view factor explains whether a surface can see itself. For convex and flat surfaces, the emitted radiation does not return to the same surface, so the value is 0. For concave surfaces, some radiation can be reflected back, so the value is non-zero. This concept is important in cavity or enclosure analysis. It allows internal geometry effects to be included in radiation calculations. Concentric spheres view factor. For concentric spheres, all radiation from the inner sphere must strike the outer sphere. Therefore, the view factor from the inner to the outer sphere is always equal to 1. This system is a perfect enclosure example. No radiative energy is lost to the surroundings. This case is very useful for simplifying multi-layer spherical system analysis. View factor geometries. Different geometries have different view factor relationships. For aligned rectangles, the aspect ratio and alignment are the main factors. For coaxial disks, the radii and separation distance are critical. For perpendicular rectangles, the height and width ratios along the common edge are the key parameters. Tables and charts are used to simplify practical calculations. Answer: B. The radii of the disks and their separation distance. Explanation of incorrect answers. A. Incorrect. Aspect ratio and alignment influence view factors for parallel rectangles, not coaxial disks. C. Incorrect. Height and width ratios affect view factors for perpendicular rectangles with common edges, not coaxial disks. D. Incorrect. View factors depend on geometry, not material properties, as they describe geometric radiation interaction. 2D view factor geometries. Two-dimensional geometries allow simplification of view factor calculations for several engineering cases. For parallel plates, the widths and the separation along the perpendicular midline are the main parameters. For inclined plates, the angle between the plates and the common edge determines the radiation interaction. For three-sided enclosures, triangle geometry and plate widths control the radiation distribution. This approach is widely used for infinitely long systems or two-dimensional approximations. View factor chart for parallel rectangles. This chart is used to determine the view factor without performing direct integration. The main parameters are the length to gap ratio and the width to gap ratio. The curves show that the view factor increases as both ratios become larger. This chart is very useful in practical design work. With this tool, quick estimates can be made for parallel plate systems. View factor for parallel rectangles. The view factor between two parallel rectangles is strongly influenced by the ratios of dimensions to the separation distance. If both plates have equal size and are symmetrically arranged, the energy exchange becomes symmetric. When the length to gap ratio is very large, the view factor approaches 1. This means almost all radiation from one plate reaches the other. A smaller gap significantly increases the radiative interaction. Check your understanding. Number 3. This question emphasizes that the separation distance between surfaces has a very strong influence on the view factor. Physically, surfaces that are closer can see each other more. This increases the fraction of radiative energy exchanged. This concept is important in compact system design. Controlling distance is often the most effective way to control radiative heat transfer. View factor chart for parallel rectangles, alternative form. This chart presents the view factor relationship with dimension ratios in an alternative form. The axes and curves are arranged to make reading easier for different size combinations. The general trend remains the same, where the view factor increases as the relative plate size increases. This chart is useful as a design aid and for checking calculation results. This graphical approach saves time in preliminary analysis. View factor for perpendicular rectangles. For perpendicular rectangles, the presence of a common edge simplifies the geometry. The view factor is determined by the ratios of lengths to a characteristic width. If one of the ratios is small, the radiative interaction is also small. When both ratios become large, the view factor increases and approaches its geometric limit. This case is often found in wall corners or duct corners. Coaxial disks view factor. For coaxial disks, the ratio of radii and the separation distance are the main factors. If the upper disk radius is much larger, the view factor increases. If the separation distance increases while sizes are fixed, the view factor decreases. When the disks are very close, the view factor can approach 1. This configuration is relevant in heating systems or disc-shaped radiation sensors. View factor for concentric cylinders, graphical form. This chart shows how the view factor changes with radius ratio and cylinder length. For cylinders that are long compared to their radius, edge effects become small. This makes the radiative interaction more uniform. The general trend shows that the more similar the sizes of the two cylinders, the larger the radiative exchange. This chart allows easy estimation without lengthy calculations.
View factor for concentric cylinders to the outer cylinder increases as the radius ratio approaches unity. For the outer to the inner cylinder, the value approaches 1 when the geometry is nearly the same and the cylinders are sufficiently long. The self-view factor of the outer cylinder decreases as the inner space becomes larger. The cylinder length also plays a role by reducing edge effects. This configuration is important in reactor analysis, insulated pipes, and heat exchangers.
Check your understanding. Number 4. This question emphasizes that nearly identical geometries result in very strong radiative interaction. When the radius ratio approaches 1, both surfaces almost completely see each other. A large cylinder length further reduces end losses. This makes the view factor approach its maximum value. This concept is important for understanding the upper limit of radiative heat transfer in cylindrical systems.
View factor conservation. In a closed enclosure, all radiation leaving one surface must strike other surfaces inside the enclosure. Therefore, the sum of all view factors from one surface to all other surfaces is always equal to 1. This principle is a form of energy conservation for radiation. No radiation escapes from a closed system. This rule is very important as a consistency check for calculations.
Composite surface view factor. If a surface is composed of several parts, the view factor to that surface can be calculated as the sum of the view factors to each part. This principle is called the additivity principle. Complex surfaces can be divided into simpler parts that are easier to analyze. Then the results are summed to obtain the total value. This approach is very useful for complicated geometries.
Symmetry in view factors. If two surfaces are symmetric with respect to a third surface, then their view factor values will be the same. The reciprocity relationship also remains valid under symmetry conditions. By using symmetry, the number of unknowns that must be calculated can be significantly reduced. This makes the solution of enclosure problems much simpler. Symmetry is often used in the analysis of cylinders, boxes, and repetitive systems. Correct answer, C. It simplifies calculations by reducing the complexity of view factor determination. Explanation of incorrect options. A. It eliminates the need for view factor calculations entirely. This is incorrect because view factors must still be calculated, but symmetry simplifies the process rather than eliminating it. B. It ensures that all surfaces have the same view factor regardless of orientation. This is incorrect because not all surfaces necessarily have the same view factor. Symmetry only equates view factors for symmetric surfaces about a third. D. It assumes that reciprocity is irrelevant for symmetric surfaces. This is incorrect because reciprocity is always maintained in radiative heat transfer, even for symmetric surfaces. Symmetry does not negate reciprocity but complements it. Crossed strings method. The crossed strings method is a geometric approach to determine the view factor between two curved surfaces. This method uses the lengths of intersecting and non-intersecting strings. The difference between these lengths is used to calculate the view factor. This approach is very useful when direct integral methods are too complicated. It is fast and sufficiently accurate for many engineering applications. Radiative heat exchange. Radiative heat transfer occurs because of a temperature difference between surfaces. In this basic approach, the surfaces are assumed to be ideal black surfaces. Energy always flows from the hotter surface to the cooler one. The amount of heat transfer is determined by temperature and geometry. This concept forms the basis before moving to real surface analysis. Radiosity components. Radiosity is the total radiation leaving a surface. including both emitted and reflected components. The reflected component depends on the incident radiation and the surface reflectivity. The emitted component depends on the surface emissivity and temperature. Therefore, radiosity combines both emission and reflection effects. This concept is very important for the analysis of gray and diffuse surfaces. Radiation resistance analogy. Radiative heat transfer can be analyzed as electric current flow in an electrical circuit. In this analogy, each surface has a radiation resistance that depends on emissivity and area. Temperature acts as the driving force, similar to voltage in electricity. With this analogy, complex systems can be analyzed using circuit methods. This approach greatly simplifies enclosure modeling. Check your understanding. Number 6. This question emphasizes the conceptual equivalence between radiative heat flow and electric current. The goal is to strengthen understanding of the circuit analogy. By understanding this, radiation problems can be solved in a systematic way. This analogy is very powerful for multi-surface systems. It also helps avoid conceptual errors in modeling. In addition to surface resistance, there is also a space resistance between two surfaces. This resistance depends on the surface areas and the view factor between them. In the circuit model, surface and space resistances are arranged in series. The path of radiative heat flow can be analyzed like a layered electrical circuit. This approach provides a very clear framework for enclosure calculations. Radiation network representation. A radiation system with many surfaces can be modeled as a resistance network. Each surface is connected to other surfaces through space resistances. In addition, each surface also has its own surface resistance. This model allows calculation of the net heat transfer at each node. With this approach, complex enclosures can be analyzed systematically. Two-surface radiation network. For two surfaces, the radiation network becomes very simple and easy to visualize. The system consists of two surface resistances and one space resistance between them. Heat transfer flows from one surface to the other through this resistance network. The heat transfer rate is influenced by emissivity, area, temperature, and view factor. This model forms the basis for all multi-surface systems. Familiar two-surface arrangements. Several two-surface configurations frequently appear in engineering applications. For a small object inside a large cavity, the heat transfer depends only on the properties of the small object. For two parallel plates, equal areas and a view factor near 1 simplify the calculation. For concentric cylinders and spheres, the radius ratio becomes the main parameter. These cases provide quick solutions for many practical problems. Three-surface radiation network. When a system consists of three surfaces, the resistance network becomes more complex. Each surface has its own resistance and also space resistances to the other two surfaces. Heat transfer can flow through multiple paths simultaneously. This leads to a coupled system of equations. However, the network approach still provides a clear structure for solving the problem. Correct answer B. The areas, emissivities, temperatures, and mutual resistances between surfaces associated with each interaction. Explanation of incorrect options. A. Only the temperatures of the surfaces involved. This is incorrect because while temperatures are important, they are not the sole determinant. The areas, emissivities, and mutual resistances also significantly influence heat transfer. C. The absence of mutual resistances, focusing only on surface resistances. This is incorrect because mutual resistances such as R12, R13, R23 are crucial in defining energy flows between surfaces, making the network complex. D. The flow of energy limited to a single path between two surfaces.
This is incorrect because heat transfer in such systems involves multiple interconnected paths, not just a single path. This complexity is integral to the system's behavior. Radiation shield network. A radiation shield is used to reduce heat transfer between two surfaces. By adding one surface in between, the number of resistances in the system increases. Heat transfer now has to pass through two stages of radiation. This significantly reduces the total heat transfer rate. This principle is widely used in thermal insulation and heat shields.
Thermometer heat transfer. A thermometer placed in a fluid receives heat not only by convection, but also by radiation from the surrounding walls. If this radiation effect is significant, the temperature reading can become inaccurate. Therefore, the energy balance between convection and radiation must be considered. Sensor design and placement become very important. This concept shows that radiation also affects temperature measurements.
Radiation beam attenuation. When radiation passes through an absorbing medium, its intensity decreases. This reduction depends on the thickness of the medium and its absorption properties. Mathematically, this attenuation follows an exponential relationship with distance. The thicker the medium, the smaller the remaining intensity. This concept is important in the analysis of gases, smoke, and other participating media. Spectral absorptivity of CO2. This curve shows that CO2 does not absorb radiation uniformly at all wavelengths. There are very strong absorption peaks at certain wavelengths in the infrared region. Between these bands, there are regions with much lower absorption. This data shows that gas radiation is highly wavelength dependent. This is important for combustion and atmospheric modeling. Spectral absorptivity of CO2. This data is taken at specific temperature and pressure conditions, showing specific spectral characteristics. Higher pressure and longer path length increase the overall absorption level. This shows that the optical properties of gases strongly depend on thermodynamic conditions. This information is used in radiation calculations for combustion chambers and exhaust gases. Without considering spectral effects, calculation results can be highly inaccurate. Check your understanding number 8. This question emphasizes that gases such as CO2 have dominant absorption bands at specific wavelengths. This shows that gas radiation is highly selective in the spectral sense. This understanding is important so that gases are not treated as uniform absorbers. In engineering calculations, only certain bands are truly significant. This concept is very important in combustion and atmospheric analysis. Spectral peak value, 15 micrometers. This value confirms that one of the strongest absorption peaks of CO2 is around 15 micrometers. This peak lies in the infrared region that is very relevant for thermal radiation. The contribution of this band is very significant in the energy balance of hot gases. Therefore, this wavelength often appears in exhaust gas radiation analysis. Without considering it, heat transfer predictions can be very inaccurate. Emissivities of H2O and CO2 increase with increasing temperature and the product of partial pressure and path length. Under the same conditions, H2O generally has higher emissivity than CO2. This shows that water vapor is often the dominant contributor to gas radiation. A longer path length strengthens the radiation effect. This chart is very important for combustion chamber and hot gas analysis. Emissivity charts. These charts are used as practical tools to determine gas emissivity without complicated spectral calculations. This approach uses average or total emissivity values. Although it is an approximation, the results are sufficiently accurate for many engineering applications. This method saves time and computational effort. However, its validity limits must always be kept in mind. Correction factors for emissivities. Correction factors are used when pressure and path length conditions are outside the standard chart conditions. For H2O, the correction factor tends to stabilize after a certain pressure. For CO2, the pressure effect remains significant. A longer path length always increases the correction factor. This concept is important for high-pressure systems such as gas turbines and boilers. Emissivity charts with corrections. Using charts combined with correction factors allows more realistic emissivity estimation. This approach keeps the simplicity of the graphical method. At the same time, the effects of pressure and geometry can be taken into account. This is a compromise between accuracy and computational simplicity. This approach is very commonly used in engineering analysis. Emissivity correction in gas mixtures. In gas mixtures, emissivity correction is influenced by gas composition ratio and temperature. When the water-vapor fraction increases, the radiation contribution also increases up to a certain point. Total pressure and path length strengthen this effect. At high temperatures, the correction values tend to become more stable. This is very important in real combustion gas analysis. Mean beam length. To simplify gas radiation analysis, the concept of mean beam length is used. This concept replaces complicated three-dimensional geometry with a single characteristic length. With this, emissivity charts can be used directly. This value depends on the geometry of the system. This approach is very practical for engineering applications. Mean beam length. This table provides approximate mean beam length values for various geometries. For spheres, cylinders, slabs, and other shapes, specific scaling factors are used relative to their characteristic dimensions. This approach allows the use of chart methods without complicated geometric integration. Although approximate, the results are good enough for preliminary design. This is an important tool in thermal engineering. Correct answer, C. Up to 95% of its diameter for infinite cylinders radiating to curved surfaces. Explanation of incorrect options. A. 65% of its diameter, applicable to both infinite and finite cylinders. This is incorrect because the 65% rule applies to spheres, not cylinders. Infinite cylinders radiate up to 95% of their diameter. B. Equal to its radius, similar to hemisphere geometries. This is incorrect as this rule applies specifically to hemispheres, not cylindrical geometries. D. Determined by the volume to surface ratio scaled by 3.6. This is incorrect because this rule is used for arbitrary shapes, not standard cylindrical geometries. Cylinders follow their own specific beam length rules. References. The reference list shows that this material is taken from a well-established and widely used heat transfer textbook. This confirms that all models and charts used have a strong theoretical foundation. These references can also be used for deeper study. Students are encouraged to consult the original sources for more in-depth understanding. With this, the chapter on radiation heat transfer is complete.